the mic.
And so while Michel is handling the tech, let me say a few words. Of course, Michel barely needs an introduction here. He's a CNRS researcher, both at Collège de France and École Polytechnique, where he's also a professor. Michel is well known for having incredible expertise on a very large spectrum of computational methods for strongly correlated systems. His interest in recent years have focused in particular on the development of diagrammatic Monte Carlo techniques, which has been a big boost to the field. I already mentioned this during my lectures, but if you want to know more about these techniques, you can read his beautiful presentation, extensive presentation in his habilitation thesis, which is really beautifully written. And of course, one of his interests is the Hubbard model, actually both at equilibrium and non-equilibrium, because he's been doing also very nice work on transport recently. So he's going to tell us about what can be said with Diagrammatic Monte Carlo on the Pseudogap, and the floor is yours.
All right, well, thank you so much, Antoine, for this introduction. I do feel a bit uncomfortable because there are so many people that I had the chance to work with and help making progress there, so I don't feel like it's all been my work. I will indeed tell a bit more about the Hubbard model, and especially from the perspective of a method that we've been working on a lot, which is Diagrammatic Monte Carlo. So maybe briefly, just to set the stage, what we're generally trying to understand is the physics of strongly correlated fermionic systems. This can be both in solid-state materials, but also in artificial systems, such as ultra-cold atoms trapped in an optical lattice, as has been described by Antoine in his lectures. And typically, these systems have a very sophisticated phase diagram. This is an example here taken for the couplet family. You've seen this before, here as a function of temperature and hole doping. I don't want to go into the details, but definitely there's lots of different phases, regimes, they're intertwined, they're competing, so it's very exciting to try to understand what's going on. Some regimes are very peculiar. Also, Thomas mentioned the pseudogap. I will be discussing this quite a bit in the second part of the talk. A regime where when you look at the quasiparticles, they behave very differently according to their wave vector. They are quite well defined when they're close to pi over 2, pi over 2, this nodal region here. This is a quarter of the Brillouin zone, and they're essentially destroyed close to pi 0, this antinodal region. So what's quite impressive is that this sort of phase diagrams is actually quite generic across different materials in the couplet family. So this gives hope that there may be quite generic underlying principles. And so we want to understand what are they, how do they connect to the physics in the ground state. So to answer those, and because they're quite generic, there's hope that actually even simplified models can at least capture some of these phenomena. And obviously, the Hubbard model is a good place to start. It's been introduced a lot in previous lectures by Antoine and Thomas. We'll be working with the fermionic Hubbard model on a square lattice in 2 dimensions, and in a special case where the kinetic term only allows electrons to move between nearest neighbor sites. So keep in mind that this is maybe not the most relevant parameter regime when we want to make direct connections with couplets, but we started with this situation here. And of course, there's this local Coulomb repulsion where electrons have an energy cost if they're sitting on the same site. So even though the formulation of the model is very simple, from the computational perspective, it's a very difficult model. The Hilbert space grows exponentially with system size. If you tackle this at finite temperature with stochastic methods, you're typically hitting a very bad fermionic sign problem. Nevertheless, we do want to know what is the content of this model, what is it, what ingredients are there in the Hubbard model, and how do they compare with the phenomenology. So my goal indeed in the past years has been to try to find at least some regimes which are interesting and non-trivial where we can get controlled, exact, numerically, at least numerically exact solutions. So I want you to basically have 2 messages that I'll try to convey. The first one is that there's been a lot of progress in computational approaches, many of them. You've seen an example in a talk by Thomas. I'll be focusing on one in particular, which is called Diagrammatic Monte Carlo, which the idea is actually fairly simple. You start from your Hubbard model, create for your physical observables, like the free energy, an expansion in U. So you write a series in powers of U, and try to compute this series up to the largest possible order. And with recent developments, we can typically get to orders of 10 to 12. This allows to go in highly non-trivial regimes of the Hubbard model, where we can get controlled results. And what's nice about the method is that it addresses directly the infinite system size, the thermodynamic limit. This is one of the peculiar aspects of this method. And for the regimes relevant for us, so values of U around 6-ish or so, we can go down to temperatures about T 0.07 in units of the hopping, which, as you've heard in previous lectures, is very much where also cold atomic experiments are sitting right now. Then using this, we can actually address the physics of the dope Hubbard model, and I'll show you controlled results for the spin and charge response in a fair part of the parameter regime in U and doping. We can carefully compute spectral functions and address where is it that we see a pseudogap. And especially, I think an important result is that we can have a handshake between what we find at finite temperature and what other methods find at 0 temperature. Of course, none of this would have been possible without important collaborations. So a lot of what I'll show today has been driven by Fedor Szymkowicz, together with Riccardo Rossi and Antoine Georges. The content is mainly in these two papers here, but it also builds on a lot of previous work with many collaborators. I'm going to forget many, but I'd at least try to spot the ones that are in the room so that I don't get in troubles. Olivier Parcollet, Wei Wu, Genia Kozik, Alice Moutner, Ono Gariou, Yaksha Vucicevic, Felix Werner, and Chris van Hauke, and others, so thanks for that. All right, so that's my plan. Let me start describing a bit the Diagrammatic Monte Carlo method and tell you a bit how it works. Again, the idea is fairly simple. I start from my Hubbard model. I will be focusing here only on equilibrium properties at finite temperature on a square lattice, but infinite lattice. And the idea is to try to write for physical observables a series expansion in powers of U. So this observable can be double occupancy, a green function, anything. And the game is to try to find these coefficients AN. If you remember your textbook quantum many-body, the content of these coefficients is actually a sum of Feynman diagrams. But behind every diagram, there's actually a big sum over many vertices here, spatial and time. So this is very difficult to be carried out, and this is typically done stochastically using a Monte Carlo method. So this is what has been proposed very early on by Nikolai Prokofiev and Boris Svistunov. And in the first versions of this algorithm, which is sometimes called Diag-MC, the way this was working is that the Monte Carlo sampling was basically moving in this space of diagrams, sampling what are the most relevant Feynman diagrams that contribute to these coefficients of the series expansion. This, however, does face a fermionic sign problem in the sense that from one diagram topology to another, even if the vertices, space and times are fixed, different topologies may have different signs. So this typically leads to a big variance on your result. Also, the internal integration over imaginary time may also have its own sign problem. So quite a bit of progress. I mean, at that level, we could typically compute 6 to 7 perturbation orders. Now, a lot of progress has been achieved thanks to a very nice trick by Riccardo Rossi in 2007, which is to say, okay, is there a way to reduce the sign problem by explicitly summing all topologies that rely on the same vertices? Okay? So this can only reduce the sign problem, but it's computationally, in principle, very expensive because for a set of vertices at order n, there's a factorial number in n of those diagrams. So this is very expensive. But what Riccardo figured is that there's a clever way to do this in exponential time by using a clever recursion and determinants. And this can be achieved in exponential time. It's not great, but it's much better nevertheless, going like 3 to the power n, where n is the perturbation order. And thanks to these developments, we can now typically go to 10 to 12 expansion orders. Let me mention that this is one approach. There's many other works taking different approaches, either looking at different families of diagrams or working in real time. You'll hear more about Olivier Parcollet. So this is, one line of approach to this problem, but there's many other works going on. So what are the pros and cons of this approach? Suppose I get these coefficients, so I do have 10 to 12 perturbation order coefficients. Well, the pros are that, in principle, if I'm able to resum this series and get a result, I do get a result for the infinite size system. This is a very powerful feature of the method. It's also, in principle, quite versatile. The difficulty, though, is that I only have 10 to 12 perturbation orders, so I need to resum this series, and typically the underlying function that describes a physical observable, let's say this n of u. This is taken in a case where I can get an analytical solution. This is just taking one side of my Hubbard model, and I see this as a function of u taken as a complex variable. So this is the complex plane in u, and I look at n of u, and typically this has poles. So these things that you are seeing here are poles in the complex plane, and those, the closest pole to the origin, defines the convergence radius of your series. So the difficulty is, well, if I'm interested in values of u inside the convergence radius, maybe the resummation will be easy, but if I'm outside and my physical point of interest is outside this convergence radius, well, this will be more and more challenging. So this is what's really difficult in the method, and the key challenge, knowing that we only have typically 10 to 12 orders. So how do we make progress? Well, of course, there's lots of mathematical tools that deal with this situation and try to resum series beyond their convergence radius in trying to change the structure of the complex plane, for example, using conformal maps, or there are other tricks like Padea approximants and so on, but they're actually quite limited. And the main progress came from a slightly different observation, namely that we do have some freedom in choosing the starting point of our perturbation theory. So the idea is basically that the perturbation theory is constructed from a bare propagator. The natural choice for this is to take a propagator which is free electrons with a certain momentum k at the physical chemical potential. But there is actually a freedom to artificially change the chemical potential by a shift here that we call alpha. So the trick is also always, often called the alpha shift trick, where we modify the bare propagator and create a new perturbation theory starting with this modified propagator. But of course, we need to balance for the fact that we have introduced this shift and introduced counter terms. But it turns out that this is actually quite easily done within the CDAT algorithm. Now, what that does in practice is that it does change the structure, the pole structure in the complex plane of your physical observables as you tune or change the value of alpha. So this is now taken an example again for just a single atomic site of the Hubbard model, a computation of the self-energy at the first Matsubara frequency, and for this particular value of alpha, you see there's lots of poles, and typically there are poles inside the radius where you want to evaluate your function. So if you look at the corresponding partial sum, this is the sum taken from coefficients 1 up to coefficient n here. This looks like it's going to be very difficult to resum indeed. Now let us change this value of alpha and see what happens. And what happens is that the structure in the complex plane changes, the poles reorganize, and in that case go further away from the origin, and at some point even go far enough that they go out of the radius here, and that your partial sum now becomes much easier to resum. Note that if you move alpha further and further, eventually some poles get closer again, and your partial sum becomes difficult to resum again. So there is some optimal value of alpha where it seems that we actually have an easier time resumming of our series. So let me show concretely how these improvements look like now for the Hubbard model itself. So this is an example from a work together with Wei Wu and Zhenya Kozik, taken at u equals 4t. There's a t prime. This is the only time you're going to see a t prime here, but there was a t prime in that case at a fairly high temperature. So if you take no shift and take your original series and compute a physical observable, this is the self-energy taken at different Matsubara frequencies. So the black line is the first Matsubara frequency, second and third. So you see, this is the partial sum as a function of perturbation order. If it were about this Matsubara frequency, well, it looks like this is something that I could resum reasonably well. But if I look at the first Matsubara frequency, there's very little hope that I can get a result from this partial sum here. If you tune alpha cleverly, well, you can get to a situation where this turns into those curves where the partial sums actually converge quite nicely. So that's the sort of improvement that we can get in favorable cases, and that allowed us to make quite a bit of progress in this method. Let me also mention that this idea of shifting the bare propagator of the action has been the source of many other works, which, among others, allow to enter ordered phases, and actually there's been quite a number of works in this direction. All right, so much for the methodology. Let me turn to the physics of the two-dimensional Hubbard model. And before anything else, I'd say that, okay, the parameters that we're looking at are basically temperature, U, the coupling, and doping. And there's two classes of computational approaches. There's algorithms that are really tuned at 0 temperature. And in recent years, I think there's a convergence of these different approaches that agree and come up with a picture which basically tells you, and Antoine has been describing this, that the ground state, if I focus at a finite value of U and start to introduce doping, the ground state is a stripe phase. So it's both a charge and a spin density wave. As a cartoon, it's something that looks like this, where the spins are basically antiferromagnetically ordered with an envelope which is slightly incommensurate. And at the nodes of these envelopes is where the holes have a tendency to gather and form these stripes. As you increase doping more, eventually this stripe disappears and you get into a different state, which may be superconducting or a more conventional Fermi liquid. Now at finite temperature, of course, the idea that this ground state has stripes triggered a certain number of studies which asked, okay, are there extinguishers of those stripes at finite temperature? And there's been different methods that looked into this problem, but I think the situation there is not quite as clear. The picture still needs to be completed, and that was a bit the focus of our work. What can we exactly say about the charge and spin response at finite temperature? And also, how does this relate to the single particle properties, the pseudogap and the spectral function? So that's a bit what we wanted to study. So let me start with the charge and the spin response. So we carefully looked at the parameter space here, U and doping, and all of these points are points where we obtained results. So we scanned quite a bit of the phase diagram. And for every of these points here, what we can typically compute is the spin and the charge susceptibility. This is an example for the spin susceptibility taken at 0 frequency. But then you see it has a very fine momentum resolution. For this particular example, you see that there's 2 peaks that are slightly away from pi. So this describes incommensurate magnetic correlations. And by fitting those peaks by an Ornstein-Sonnecker form, we can actually extract a typical correlation length of this magnetic fluctuation. So if we do that and look at the parameter space U and doping, here's what we find. So let me first focus on this column here. This is taken at fixed temperature. And we look at the susceptibility, the spin susceptibility, at the point where it's maximum, okay, as a function of U, and every curve corresponds to a different doping level. This is the same for the correlation length, and the message is more or less the same. What we observe is that at first, when you start from small coupling, the correlation length or the spin susceptibility increases. It reaches a maximum at around U5 to 6-ish, and then goes down. And the closer you get to have filling, the stronger this response. So this, taken as a color plot, is basically shown here. So the color is the correlation length, red is longer correlation length, and what you see is that the closer you are to have filling, typically the longer the magnetic correlation length. As a function of U, it first is the correlation length increases, gets a maximum, and then decreases. So what we see is 3 regimes. There's a small U regime, I would say for U smaller than 3, where the magnetic correlation length is fairly small. And if we look at the charge response, which I'm not showing here, we see that there is a weak Pomeranchuk effect where the double occupancy increases with decreasing temperature. In the intermediate U regime, the magnetic correlation length is long and increases here. This is this regime, and we definitely see a decrease in the entropy that we can also compute because the system is starting to get quasi-ordered. And as we increase U more, we have a strongly correlated regime where the correlation length becomes short again. Very good. Let me just mention that the spin response is very sensitive to temperature. So this is now taken for different temperatures at a fixed doping. And you see that decreased temperature, the spin response becomes stronger, and so does the corresponding correlation length. I can go a bit deeper in the analysis and ask, okay, if I want to say something about the stripy behavior or the possible stripy behavior of this regime, what is the magnetic response? Is it commensurate or incommensurate? How does this change with doping and U? And here's an example here at fixed value of U as a function of doping. In the beginning, the magnetic response, here this is the spin susceptibility is at pi, so it is commensurate. And as you increase the doping, eventually this peak splits into two pieces. The magnetic response becomes incommensurate. And this is something that we typically see as we increase doping. So the red region is antiferromagnetic and then becomes incommensurate as we increase the doping away from half filling. But it's also a phenomenon that we see as we increase U. So the larger U, the more incommensurate the response. So in the spin sector, it seems that we start having ingredients to have a stripy response, but we need to see what happens in the charge sector as well. And there, actually, the situation is very different. So this is a computation of the charge response, of the charge susceptibility, taken close to 0 along the 0, 0 pi line. If there were really a stripe, we would see two clear peaks appearing close to 0 with a vector connected to the commensuration vector of the spin response. At those temperatures, this is 0, 1, and this even at the very lowest temperature we can reach, this response is extremely weak. It's actually hardly stronger than the response of free electrons for this system. Also, the behavior of the charge response as a function of U and temperature is drastically different from the spin response for the same parameters. There's almost no temperature dependence, and there's no maximum seen as a function of U. So at least in those parameter regimes that we could investigate up or down to those temperature T 0.07, there's very little evidence of a strong charge response or a stripy behavior. All right, I am bad on time. Let me switch to single particle properties and see how all of this connects to the single particle response and the spectral function in general. So again, we scan the same parts of the phase diagram in U and doping, and this is an example of what we can extract. So this is a spectral function here taken again over a quarter here of the Brillouin zone. That's the gamma point pi, 0 pi. And so this is an example where we see that there are more coherent quasi-particles close to the node and more incoherent ones close to the antinode. So this is a pseudogap regime. And we needed some criterion to be able to decide, oh, when is it that we have a pseudogap? Just looking at the spectral function, this is not entirely obvious. So one criteria that we use, we've used several ones, but one that we've used is to actually look at the self-energy. So we can also compute the self-energy, the correction to the Bear-Green's function. And what we see especially is that if we look at it as a function of Matsubara frequency, this is starting to be a bit technical, but it's just for aficionados, we have regimes where the self-energy, the Matsubara frequencies go down towards 0, which is more a metallic behavior, and we consider that this is not a pseudogap regime. And there are regimes where this instead has a turn down, which is more insulating-like. And the moment this self-energy turns and changes sign, we observe this here in such pictures where the red means that the slope has changed. And the moment we observe this change of slope, we say, okay, this is where we have a pseudogap regime. So we can map that carefully for our results. So that's at the fixed temperature here, T025, as a function of U and doping. And this is the results that we find. So there are three regimes that we observed. There's a regime at small values of U and larger doping, which is a weakly correlated metal. The metal there, the Fermi surface, if you look at it from its spectral properties, or again from an empirical definition of the Fermi surface by looking at the maximum of the spectral function, we basically see something which is very much like the non-interacting system. And in that case, that means we have an electron-like Fermi surface, which is what you expect if you whole dope your system. Okay? If I go at larger doping and start increasing U, the system remains metallic, but there starts to be strong deformations of the Fermi surface. And there is a critical point, or a point where suddenly the Fermi surface switches from electron-like to hole-like. There's a Lifshitz transition into what we call a strongly correlated metal, where there are strong effects on the fermiology of the system. As you get closer to half filling, the correlation effects even get stronger, and eventually a pseudogap appears. And this is, according to our criterion, the line where the pseudogap appears. Let me notice that these lines here are lines of equal magnetic correlation lengths. So there's definitely a regime of pseudogap where the correlation length is very long, sort of a weak coupling pseudogap with long correlation lengths, but there's also definitely a pseudogap at strong coupling where the correlation length has again become shorter. It's still present, but it's shorter. Okay, so let me maybe flash some spectral functions that are obtained in the different regimes. So at weak coupling, so if you're in the weakly coupled metal here, what we obtain for the spectral function, as you see, is a well-defined Fermi surface, and the maximum is electron-like, as expected for a weakly correlated metal. The self-energy is quite small if you look at the scale, and there's nowhere where we see a bending of the slope of the self-energy. This is a good metal. If I go to the strongly correlated metal S, this is this line. Again, no pseudogap at this point. The self-energy starts to be a bit stronger, strong enough to deform the Fermi surface, which now, if I track the maximum, has become hole-like. In a pseudogap, we start seeing places where the self-energy slope has changed. Quite in general, the self-energy has become much bigger and starts displaying pole-like structures just above the antiferromagnetic Brillouin zone, here close to pi0. In both cases, both in the weak coupling and also in the strong coupling. And this is what destroys the quasi-particle coherence here close to the antinode and also reshapes the Fermi surface a lot. Let me mention that we try to see what is finally the mechanism behind the pseudogap. It seems clear from looking at this diagram and remembering the one that I shown for the spin response in the system that there must be a strong connection between antiferromagnetic correlations and the pseudogap. And actually, if we take a simple spin fluctuation theory and try to fit this data to see whether we get a reasonable agreement, it's actually not too bad, albeit the fact that we needed to give some more freedom in the spin fluctuation fit, namely give us some freedom about the effective chemical potential that we use in our Baire propagator in this spin fluctuation formula. Great.
So pi gets pi pi?
Say it again?
The capital pi, is that connected?
That's pi pi, yes. Is it?
And omega 0 is pi t? What is omega 0 here?
Wait, no, what is this pi here? Yeah, this must be pi pi.
Okay.
Yes.
And omega 0 is just pi t? Yes.
Yes, exactly. That's the first Matsubar frequency, and that's pi pi. Yeah.
Okay. You can plot for n of k or some Fermi surface things?
I mean, the Fermi surface information is in G0. So.
Okay. Yeah.
All right. Yeah, this is indeed taken at the first Matsubar frequency. So this is not taken at, if you want, at omega 0, where this would indeed be more directly connected to NF. Yeah, sorry. Great. Last but not least, in the time that's left, we've investigated how this picture changes as we decrease temperature with the goal of seeing how this connects with the Euro temperature results. So this is what I've shown earlier. When we decrease temperature, we basically have the same picture, but the pseudogap region starts to increase, which is expected as we lower temperature. Correlation effects are stronger, the pseudogap increases, and we've tried to extrapolate the boundaries of these different regimes to zero temperature. And what we find, quite surprisingly, it's very striking, is that our extrapolations, which are taken here, so this is our extrapolation at t equals to 0 in the U doping plane, and this red line is the extrapolation of the pseudogap regime. And this matches very closely to the line found in zero temperature methods that separates the stripe phase from the non-stripy phase. Actually, the line here is the black line here. It's almost on top, and I want to emphasize that we found this red curve before we had the black data. So this was actually an honest extrapolation. Great, so this seems to be saying that as we decrease temperature, eventually the pseudogap regime becomes unstable and turns into a stripe state at lower than zero temperature. So to conclude, I want to say that, well, there's, I think, been a lot of methodological progress I've shown here results from Diagrammatic Monte Carlo, but there's other methods, and they sort of give us now a coherent picture of what's going on. I think it's clearly established that in a Hubbard model, we do have a pseudogap regime whose origin, at least at intermediate temperature, is definitely spin fluctuations. This pseudogap regime extrapolates exactly to the place where in the ground state we see a stripe. As we increase the doping, we have first a correlated metal with a modified Fermi surface and eventually a more conventional metal. Now there's lots of questions remaining. One of them, and that is giving us quite a bit of a headache right now, is how does this pseudogap eventually turn into a stripe? There must be a phase transition. It is actually allowed at finite temperature. How does this happen exactly? And there are first works, especially this nice work by Boschau, that do see first indications of a phase transition between the pseudogap regime and the stripe phase. We're trying to find the same in Diagrammatic Monte Carlo, but we're challenging, I mean, we're just in a regime that is really difficult for us, the temperatures that we just can't reach. Of course, to make connections with cuprates, it would be nice to also have a T prime to be closer to cuprates physics. So this is also something that is going on. I have quite a bit of interest, as Antoine was mentioning, into trying to understand more about the transport, something that I'm doing with Yaksha Vucicevic, who's here. And of course, the elephant in the room is the superconductivity. Can we get there? Can we say something about this? So those are all the projects for the future. And with that, thank you for your attention.